I'm going to be happy to introduce Aditi Sheshadri from Stanford University. So I've known her for a number of years. So she got her PhD at MIT working with Alan Plum, and I had been a colleague of Alan's and had gone to visit a number of times when Aditi was a student yet, and that's how I got to know her. And you may not remember this, but you were one of the people that took me out to lunch. Yeah, it was a good time, good lunch. And maybe to dinner also, I can't remember. But so then she got a PhD in 2015, and she went to Columbia University. You was a Simons Fellow or something like that, and worked with our friend Lorenzo Polvani for a number of years. And then since January 2018, she's been a faculty member at Stanford University in the Department of Earth System Science. Is that right? Yeah. And she has experience in large-scale dynamics, climate variability. She's worked on the polar vortex. Today she's going to tell us about storm tracks and large-scale variability in storm tracks. So, Aditi, welcome.
All right. Well, thank you so much for inviting me to come give the seminar. I guess I kind of invited myself because I'm here for the UCAR members meeting tomorrow, but it's kind of the same thing. Thanks for showing up. I'm going to be talking to you today about two things, both concerning mid-latitude jet variability. The first is going to be sort of a zonal mean perspective on things, and the second will be zooming in on the North Atlantic basin. And they both have something to do with how mid-latitude jet variability can be forced from above and below, by which I mean from above because of variability of the stratosphere, and from below because of forcing by things like large-scale topography. So the first part of my talk is something I've been thinking about for, maybe 2.5 years now. And it's this really intriguing idea that we might be able to say something about how a dynamical system, such as the climate system, might respond to forcing using nothing other than observations of the unperturbed system. So we have about 35 years of reasonable atmospheric observations, such as, for instance, winds. Can we use nothing other than that to say something about how the atmosphere will respond to forcing by, for instance, greenhouse gases or ozone depletion? Or if you take a model and you do something very, very simple, like hit it with a torque, or you put in like a patch of Gaussian heating or something, how will the model or the atmosphere respond to those forcings? Is there something common to how it responds to different kinds of forcings? So a more scientific way of saying all of that is, can we identify preferred modes of response of the climate system? The second question here will become clearer as I go through the talk, and why I'm going to call them propagating modes will also become evident, I hope. And the second part of my talk is going to zoom in from this zonal mean picture and focus in on the North Atlantic and answer sort of a similar question, really. There's been a bunch of literature that suggests that there are preferred positions of the jet stream in the North Atlantic. So we're going to talk a little bit about what sets those positions, where they are, and why can't all of these CMF models ever get them right. So going back to the first part of my talk, I will get through the method in a slide and a half, I promise. You don't really have to follow any of this if you don't want to, it's fine. So if you have a dynamical system, such as the climate system, and you're interested in understanding the variability of something associated with that system, let's just call it X. Think of X as zonal mean, zonal wind for now. And there's an equation that looks something like this that describes the variability of X. L here is just some linear operator, N is some nonlinear operator, and F is some forcing. And we want to simplify this a little bit more, and we say that we're interested in the fluctuations of X about some mean state of the system. So for us, that would be the climatology. So if you take this and take out the seasonal climatology, we end up with an equation that looks a bit like that. And we want to further simplify the crap out of this. We say that we're interested in the steady state response to a steady state forcing, so no time dependence. That term goes away. So we can write the mean response to steady forcing as just X is A inverse F. A here is the system operator associated with this with this dynamical system that we're concerned with, namely the climate system. So far, so good. The trouble is that the atmosphere is a chaotic, turbulent system which contains all of the inherent complexities of Navier-Stokes, or whatever simplification of that we wish to solve. And so it contains inherently eddy feedbacks at different length scales. And despite decades of research, we really have no idea of what these eddy feedbacks are. And so in order to get the response of X to some forcing F, we have to invert this operator A without actually knowing what it is. So that seems to be a somewhat non-trivial problem. However, there is a theorem known as the fluctuation dissipation theorem that tells us that we can reconstruct the soul, if you will, of this system operator A from another operator, a matrix that I'm going to call G of tau over there. And G of tau is constructed from the lagged correlations of the unforced system. So think of it as what does the wind look like on day X? How is that correlated with the winds on day, say, X plus 10 or X minus 10 days? And one other detail that I should mention is that I do this in EOF space. Atmospheric people are probably all very familiar with EOFs. They're just an SVD, a singular value decomposition of whatever matrix that you want to come up with. I can write that down if that helps. So supposing you have fluctuations of X in this big matrix, you can decompose this into 3 other matrices, and the columns of this matrix are the EOFs. The columns of that matrix are the PCs, and this matrix contains singular values, sigma 1, sigma 2, along the diagonal. Everybody somewhat familiar with this? A few nods, so I'll move on. So this is done in EOF space, and it's a little bit important to mention that there is no truncation. All of the EOFs are used. So the lag correlations of every EOF with every other EOF go into this analysis. This is really only about 5 lines of MATLAB or 5 lines of Python, and the 5 lines of MATLAB are yours if you'd like them, so please let me know. So now the eigenvectors of this new matrix G of tau are identical to the eigenvectors of the system matrix, of course under some simplifying assumptions. The eigenvalues of G of tau are not identical to the eigenvalues of A. However, they're very simply linked to the eigenvalues of A by the simple exponential dependence. Now, in theory, having done this, reconstructing the response of X to any forcing F is actually somewhat simple. You just do it mode by mode. So we have this whole set of modes, and so the response Xn in any mode n is a product of 2 things. The first is the inverse eigenvalue associated with the mode, and the second is the scalar projection of the forcing onto the mode. So this is a good analogy for this, really, is like hitting a bell. If you hit a bell, it rings like a bell. It doesn't matter how or where you hit it. It always rings the same way because it's got these modes. So think of your favorite physical system with eigenmodes. For instance, think of a string fixed at both ends. It's going to do that, it's going to do that, etc., etc. So we're trying to come up here with eigenmodes of the climate system. Please interrupt me if you have questions, by the way. It's much better that way. So this brings us to the so-called annular modes that have been ubiquitously used in climate research. This is the first paper that I know of, at least, that introduced the concept of an annular mode. So what we're looking at here is the first EOF, the first column of this matrix U, that comes from lining up variations of anything you wish, like geopotential height or zonal mean, zonal wind, or whatever, and you take an SVD. The first EOF that comes out of that analysis has been known as the annular mode. And in both hemispheres, so we've got southern hemisphere on the left, northern hemisphere on the right, latitude on the x-axis going up, or down in pressure up in the atmosphere on the y-axis. So in both hemispheres, the leading EOF looks pretty much like a dipole, so positive, negative. And the dipole straddles the mean position of the mid-latitude jet. So if you think of the EOF of this EOF, what it's describing, left to itself, is small variations in the latitude of the eddy-driven jet. At the bottom is the longitudinal structure of this EOF, and they're referred to as annular because they're somewhat zonally symmetric. They're not quite zonally symmetric, particularly not in the Northern Hemisphere. There's a friend of mine that talks about how the modes aren't really annular because they're not quite zonally symmetric. I'm going to try and convince you that they're not really modes either, in that they're not physical modes, eigenmodes of the underlying dynamical system. So they're actually neither annular nor modes, but they have come to be described as annular modes. Did I hear a question? Or? No, I didn't. Okay, and the time scale associated with the decorrelation of the first EOF has been used to evaluate and categorize climate models. And the idea there is that if a climate model has an annular mode timescale that is too long, it's going to over-respond to things such as CO2 or ozone or whatever. Now, annular modes are purely statistical. They come from an SVD. They contain no dynamical information because there are no lagged correlations. Additionally, annular modes are constrained to be orthogonal to each other because they come out from an SVD, as I've already said. Now, what I am trying to get at is a little bit different than that. So just in case you're not familiar with EOFs, you can get EOFs of anything. Like you can take this picture, line up a matrix of zeros and ones based on the black and white pixels in this picture. So this is Feynman sitting at a desk, of course. Here is the first EOF, the first 2 EOFs, the first 10 EOFs, and the first 50 EOFs. So just to make the point that you can take an EOF of anything, and it isn't telling you anything inherent or dynamical about the system, you can do this with any matrix you like. Now, what I am trying to get at is something more like this. So if you take a tuning fork, now this tuning fork has these preferred modes of responding to whatever you hit it with. Now, of course, you could break the tuning fork, in which case none of this is valid, but if you want to keep the tuning fork alive and well, these are its preferred modes of response. So these are the eigenmodes of the tuning fork. So what I am trying to get at is something very much more like this, or at least an approximation of something very much more like this. Now this brings me to something else. This is again the first instance that I know of this. This is an old, well, somewhat oldish paper now by Steve Feldstein. What we're looking at is 150 days. This is a Hofmüller diagram with days on the x-axis and latitude, 0 to North Pole and 0 to South Pole on both of these. And these are integrated zonal mean, zonal wind anomalies across the depth of the troposphere. So going from the surface to 100 hectopascal. And this is a ubiquitous feature of both observed and modeled climates. You see these patterns of forward propagating zonal mean, zonal wind anomalies of both signs. So they propagate from about 20 degrees north to about 60 degrees north over the period of a few months. And you can see this in the Southern Hemisphere. So I've actually looked at the Southern Hemisphere now year by year, and you see it 3 out of 4 years in the Southern Hemisphere. In the Northern Hemisphere, it's a tiny bit more complicated because the two basins behave differently, but you see it in the Northern Hemisphere as well. And a single EOF cannot be expected to capture this sort of time dependence of zonal mean, zonal wind anomaly propagation. So let's go back to the EOFs now. This is era interim 79 to 2015 or something. And here's the first EOF as before. We see a dipole, of course. The second EOF is a tripole with its primary extremum being coincident with the position of the mid-latitude jet. So if you think of these as independent modes of variability, the first is describing small fluctuations of the jet about its mean position. The second is describing the so-called pulsing mode of variability, changes in the strength and the width of the jet. They have different decorrelation timescales. So in era interim, it's about 11 and 8 days. And the EOFs are constrained to be orthogonal to each other, and the PCs associated with the EOFs are again constrained to be orthogonal. But if you look at their lag correlations, they are indeed 0 at lag 0 because they have to be by definition. But they have small but significant lagged correlations at a lag of about 10 days. And the sense of these lag correlations is that the two PCs and the two EOFs associated with them are in quadrature. So they're cycling through each other. Positive PC1 is leading into positive PC2, is going into negative PC1, and so on. So they're in quadrature. This picture is even clearer if you look at a simple perpetual-winter idealized model integration. So this is basically held in Suarez with a polar vortex stuck on top of it. And it's in perpetual winter conditions, so I don't have to deal with any seasonality. And it's a very long integration of this model. Again, here's EOF1 and EOF2, and here are the lag correlations. So there's small but significant lag correlations again, here at a lag of about 20 days or so. And it turns out these two EOFs in quadrature are actually describing the polar propagation of these zonal flow anomalies that I talked about. On the top again is a Hofmüller diagram. This is 1,000 days from the model, integrated zonal mean, zonal wind anomalies across the depth of the troposphere. So you see both negative and positive signed zonal mean, zonal wind anomalies propagating forward. And at the bottom is the same thing reconstructed from the two leading EOFs. So the two leading EOFs are describing the systematic forward propagation of zonal mean, zonal wind anomalies. This is just a 1,000-day snapshot from the model. Any other 1,000 days looks pretty much the same. Now, instead of looking at EOFs, if you go through the process that I talked about earlier and calculate the eigenmodes, and now it's going to become evident why I call them the propagating modes, I'm going to call them the POPs, the principal oscillation patterns. There's some literature on POPs, even in the atmospheric context. But on the top here is EOF1 and EOF2, both of which you are now familiar with. And at the bottom is the leading POP that pops out of the analysis. I'm used to getting a laugh when I say that, by the way. So the leading POP that pops out of the analysis that I talked about is actually a pair of complex conjugate propagating POPs. So they come out of an eigenvalue decomposition of a real matrix, so you can get decaying modes, but you can also get propagating modes with complex conjugate real and imaginary parts. And the propagating modes have two timescales associated with them. The first is a timescale of decay, which comes from the real part of the eigenvalue. And then there is a period of propagation of the mode that emerges from the imaginary part of the eigenvalue. Now, the real part of this POP looks quite a bit like EOF1, and the imaginary part of the POP looks quite a bit like EOF2, which is kind of magical given that the cross correlations of every EOF with every other EOF went into this analysis. But also, on the other hand, one must remember that the first two EOFs describe quite a lot of the variance, and so perhaps it's not that surprising. The other thing to be pointed out here is that the timescale of decay of the POPs, which is 39 days here, is very much longer than the decorrelation timescale of the first EOF, which is 19 days in this model. So anything that evaluates the climate response or looks at eddy feedback or anything like that is probably a little bit inaccurate because the mode actually sticks around a bit longer than the EOF would assume that it does. So far, everything that I've shown you has been purely tropospheric. As Bill mentioned, I was brought up by Alan Plumb, and so I have to talk about the stratosphere. EOFs have also been used to understand how the stratosphere and the troposphere communicate with each other, and how the polar vortex and changes in the polar vortex strength can influence the jet. Here is just a schematic representation of that. So when the polar vortex becomes weaker, typically we expect the tropospheric jet to shift equatorwards. I like to show this because this was my last winter in Boston. I think there were two significant polar vortex events that winter. They piled up the snow. This is an undergrad dorm back there for scale. And they piled up the snow right in front of the undergraduate dorm. This is in May, by the way. And these are some very triumphant undergrads who have scaled the snow mountain. A more technical way of describing this is to look at the first EOF again. So here is This is from a review paper by Kushner. It's 50 weak vortex events. And what we're looking at is values of the annular mode, anomalous values of the annular mode. And you see that these anomalous values of the annular mode appear to progress downwards, where they stick around for between a month to 2 months, following when they first become evident in the stratosphere up here at 10 hectopascals. Now, there appear to be two issues with this way of examining this. You can get EOFs in two ways from atmospheric data. You can do it level by level, or you can do it for the full atmosphere. Now, if you do it level by level, the sign of an EOF is purely arbitrary. So if you get an EOF for one level and you get an EOF for another level, if you multiply the EOF by -1 and its PC by -1, you change nothing. So saying that the sign of this is the same as it progresses downwards isn't quite accurate, because you could multiply any of these by -1 and flip it. So inferring sort of causality across the tropopause using this appear to be a little bit dodgy. Now, if you want to calculate the EOF for the full atmosphere, for the deep coupled troposphere-stratosphere system, you have to make a choice on how you weight your data before you get the EOF. So you can either weight by mass or pressure or not. So here is the mass-weighted EOF1, EOF2 below. And I'm going to toggle back and forth and show you what the EOFs look like without the mass weighting. So with the mass weighting, the first EOF is basically picking up tropospheric variability. And if I do it without the mass weighting, it is basically picking up stratospheric variability. On the left is the leading pop, or on the right, sorry, that emerges from this analysis. This is the real and the imaginary part. Now, if I go back and forth, you see that the EOFs change in structure, but the pops do not. And it's possible to show this analytically. If you care, you can look up the appendix of my paper. But pops are independent to how you weight your data. The eigenvalues and the eigenvectors look identical whether or not you weight your data with pressure or latitude, whatever you want to do. So the pops can actually be used to look at the coupling of the deep troposphere-stratosphere system. The other reason that they're kind of cool is that you can use them to look at the time structure of these zonal-mean, zonal-wind anomalies. This is a Southern Hemisphere-like situation in a model, Perpetual-winter. Play that again. There we go. So you see these systematically forward propagating zonal mean, zonal wind anomalies of both signs. The black contours there are the climatology, and the arrows are the EP flux anomalies associated with this propagating mode. This is a Southern Hemisphere-like situation. Now, if we do the same thing for a Northern Hemisphere-like situation, here is the leading tropospheric mode again, where you see this forward propagating anomalies. Now, if we look at the leading stratospheric mode instead, which for some reason has stopped playing, I always have trouble with these videos. You see that both signs of polar vortex variability, both the positive and the negative, both anomalously strong and anomalously weak vortex events, appear to show anomalies that progress down all the way to the surface. And this is very consistent with vacillation cycles in the stratosphere. You can also see, if you look at the arrows that aren't moving, that there's a lot of upward propagating wave activity. The polar vortex then weakens, and then there's anomalously downward wave activity, and it goes back and forth. But this is really nice, I think, because you can use this to look at the full deep coupled troposphere-stratosphere system, and it shows that both anomalously positive and negative values of this mode extend all the way down to the surface. Now, there are lots of implications of all of these things. The first is that the response to a climate-like forcing or ozone depletion, or whatever you like, does not necessarily have to be EOF1-like. Now, I've demonstrated this in this model. This is a Helden-Suarez type of model, basically. The colors are EOF1. So I took this model and I hit it with a torque that looks identical to EOF1. It is co-located with EOF1. Here are the positive and negative values of the torque that I hit it with, this black and white. And here's the response. Now, if you look at the response, you would say it looks EOF1-like because it looks like a dipole. But if you actually look at the positions of the dipole, it is shifted about 10 degrees forward of the peaks of EOF1. And the reason for this is that EOFs 1 and 2 are just projections in EOF space of this complex conjugating coupled mode. And so you can't excite one without exciting the other. The ozone depletion response as well is shifted about 10 degrees forward of the EOF1 peaks, both in models and in observations. I'll skip this, although it's a really cool experiment. Well, so this is this simplified model experiment where I put in an ozone hole all year round. It's the sort of thing that I like to do. But again, the response is shifted significantly poleward of the peak of the EOF. There's the jet position. All right, so let me just summarize this section because I want to tell you about the North Atlantic stuff as well. So we've come up with a reasonably robust way, we think, of calculating these eigenmodes, pops. And sometimes the leading pop is a complex conjugate pair of pops, which describes propagating structures. So it has structure in both space and time. And their eigenvalues can be used to study climate responses. We're looking into this a little bit now. They can also be used to study stratosphere-troposphere coupling because they actually show deep vertical structures. And it seems like what it reveals is that there are separate tropospheric and stratospheric modes. Sometimes they might interact. And there are implications here for predictability, for eddy feedbacks. Isla and I were just talking about eddy feedbacks, but you can't have eddy feedback only in EOF1 and not in EOF2 because they're basically the same mode. So what's one of the things I've been thinking about. And of course, greenhouse gas responses, et cetera, et cetera. This is an ongoing area of study, so we'll see where we get with it. 257, all right, great. Switching gears a little bit, everything I've been talking about so far has been the zonal mean picture of jet variability. I'm going to focus in now on the Atlantic jet stream, the Atlantic eddy-driven jet. So here it is. The colors are from Wacom, and the black contours are from EOIntrim. So this is the thing that we're studying. And by the Atlantic basin, that's what I mean. These are the longitudes that we're going to study. And just to motivate what I'm going to be talking about, here is a movie of just daily snapshots of the winds in the Atlantic sector. The blue here is the climatology. So if you stare at it, you might come to the conclusion that there's 2 or maybe 3 preferred regions where the winds want to be a maximum. Play that again. So you can stare at it. So you can see that it's sort of eddy-driven jet-like. Sometimes you see it in the mid-latitudes, but you also see peaks up there sometimes, and you see peaks down here sometimes. So that's what we want to study. And apparently there's some literature on this, not a whole lot, but some. So a nice way of looking at these preferred positions is to look at a PDF of the latitude at which the winds maximize, the near surface winds, 850 hectopascal. This is from a paper by Woolings et al. Back in 2010. So here again is the climatology, the blue. And the black is a PDF of what Woolings calls the jet latitude index, which is what I just said. You pick out the latitude where the winds are a maximum, and you plot a PDF of that. And it seems like the impression that we got from the previous video is true. There are 3 preferred positions of this jet in the Atlantic basin. There's some explanation for this preferred position of the jet. Apparently it has something to do with blocking over Greenland. I don't quite understand what blocks are really, but that's for the future. For this talk, we're going to be focusing in on these 2 positions, because we didn't really find a convincing explanation for why there's this sort of split jetness in the Atlantic. There's some mentions of the NAO and the EA, which are all somewhat similar. They're just looking at EOF analysis again of just the Atlantic jet. So we're going to try and figure out why there are these two positions, why they are where they are, and why models don't seem to get them right. And we're going to use Wacom for this analysis. Wacom does a reasonable job in getting the PDF of Jet Latitude Index right. So the black here is the era interim, and the red is the Wacom. So Wacom sort of overestimates the peak, both the middle and the northern peaks of the eddy-driven jet, and it somewhat underestimates the peak that is apparently associated with blocking, but it gets the 3 peaks, and so maybe it's a reasonable model to start off with. And why are we focusing in on the Atlantic? These preferred positions appear to exist basically in the Atlantic. Here is the Southern Hemisphere and the Pacific basins in both hemispheres, and there's no evidence of any preferred positions in any of those basins. How does CMIP do? Here is CMIP 5. So the colors are all of the CMIP 5. The gray here is the era interim. So here's peak 1, peak 2, and peak 3. And the black is the CMIP 5 multi-model mean. The colors are all of the CMIP models. Now, without naming any names, some of these models are really pretty awful. This pink one is basically just a Gaussian. And the multi-model mean doesn't really mean anything because it doesn't seem to get anything really right, and it doesn't look like any of the models. So perhaps not the best way of thinking about PDFs of Atlantic jet variability, probably amongst other things. Okay, so in the next 20 minutes, I'm going to try and answer these questions. What causes these distinct central and northern regimes? Why are so many models so bad at getting them? And to some extent, how do these regimes respond to forcing? I was going to talk about CO2 a little bit, but maybe not. Just how do these regimes respond to forcing from above and below, which is what I started off with. How do they respond to stratospheric variability, and how do they respond to topography at the surface? So I'm going to start off again with stratospheric variability because that's something that I think about quite a bit. So here's era interim. The base mean, by which I mean just some winter mean, is this black. So you see the preferred positions of the jet. And the 60 days following sudden warming events in the Arctic is this red line over there. As you can see, there is a decreased probability of occurrence of the northern peak and an increased probability of occurrence of both the central and the southern peaks. And I think that this is a slightly different way of thinking about the Atlantic response to sudden warmings. It's not so much a systematic equator wedge shift of the jet that sticks around for about 10 days or a month or whatever it is. There is no spectral peak if you look at the Jet Latitude Index and look at its time series. However, there is a decreased probability of occurrence of the northern peak and an increased probability of occurrence of the central and the southern peaks, which seems to imply, if we believe that this peak is because of blocking, that there is an increased probability of blocking in the Atlantic following sudden warmings, which is a little bit different than what has been reported, so we need to dig into that a little bit more. Michael Goss, who is a postdoc with NOAA Diffenbaugh, but has been working with us a little bit, is working on a manuscript on this stuff. Here is Wacom. It's pretty much the same story. Again, there's a decreased probability of the northern peak and a vastly increased probability of the peak that's apparently associated with blocking following sudden warming events.
Which version of Wacom?
5. Should we be using something else?
The new version is Wacom 6. So you're using
5, yes. Okay.
The new CMIP 6 is consistent with Wacom 6.
Okay. Okay, so going back to the original question, why do these two peaks exist? We thought to begin with that it has to have something to do with planetary scale forcing. So it has something to do with some mountain range or the fact that there's land-sea contrast in the Northern Hemisphere, something like that. So we took Wacom and we flattened all the orography everywhere. And the Wacom control is back here in the black, and this is the flat Wacom, no topography anywhere. So you see that the northern peak basically disappears. There's no separate northern peak without any orography. But then which mountains matter? My collaborator on this, Rachel White, came up with which mountains matter, and she had an earlier paper saying that Mongolian mountains matter most for something else. But anyway, so which mountains actually matter for setting this northern peak? So we did a bunch of experiments. This is an experiment in which we flattened all Asian orography, so Mongolia and Tibet, we just leveled. So the red is the no Mongolia-Tibet simulation, and in fact, there is an increased probability of the northern peak without Mongolia and Tibet, so it's not that. And then we went to North America and flattened all of the orography, same deal. So without the Rockies, the peak exists, it's at the same latitude, there's a decreased probability of it, but the latitude of the peak doesn't go away, the peak doesn't go away. So the existence of the peak is not about the Rockies. Finally, we flattened Greenland. We just got rid of the Greenland ice sheet, and the peak disappears. You get more of a sort of a plateau situation. I should have mentioned this is work with Rachel White, who is now a postdoc in Barcelona, and Casey Hilgenbrink also did a significant fraction of the work. She was actually an undergraduate researcher with my advisor back at MIT, and has continued to work with me after she moved to UW for her PhD, which has been lovely. Yeah, so if you flatten the Greenland ice sheet, this northern peak disappears. And my favorite experiment so far, we picked up Greenland, moved it north by 4 degrees, and the northern peak also moved north by 4 degrees. So this was actually a bit of a disappointment to me, because I was hoping that the existence of 3 separate peaks was some complicated, some dynamical kind of a thing with like different LC1, LC2 wave breaking or something like that. But it turns out that this northern peak is just a physical consequence of the existence of Greenland. So these westerlies that come and impinge on the tip of Greenland, and there's a local acceleration sort of downstream of Greenland, and that's all that this northern peak is. If you get rid of Greenland, you get rid of the peak. And there's some mention of this in the literature. This is referred to as the Greenland tip jet. Here's what it looks like. So as I said, there's westerlies that impinge on the tip of the ice sheet. There's some local acceleration downstream of that. And what we're picking up is just these tip jet events. So the northern peak, we think, is just these tip jet events. And if you go into the reanalysis and you pull out the days where the tip jet events exist, using the definition from the previous paper, and you make the PDF again, the northern peak just basically disappears. So just to summarize, this northern regime, preferred position, or whatever, is not really a dynamical regime. It is just due to the presence of Greenland. If you flatten the Greenland ice sheet, you remove this distinct peak. If you move Greenland, the peak moves with Greenland. And if you get rid of the tip jet days from your interim, you flatten out this northern peak. Now, the question on everyone's minds is probably, why don't the CMIP models get this northern peak? They all have Greenland, right? So we have a working hypothesis on this, which isn't really published yet. But what we think it is that most models have their eddy-driven jet in the wrong position. It's either too equatorward or too weak. So the right amount and strength of westerlies aren't really impinging on the tip of Greenland to give you these tip jet events. So just to give you some, I just said it in words, but just to show it, going back to our original simulations where we flattened topography, here is the no Mongolia-Tibet run again. In the no Mongolia-Tibet run, there's an increased probability of the northern peak, and that is also consistent with a climatological eddy-driven jet that is shifted forward. It's also a little bit stronger. Without the Rockies, there's a decreased probability of the northern peak, And that goes along with a climatological DJF eddy-driven jet that is shifted equatorward. Well, this is CAM versus Wacom, but it's the same picture. Basically, if you have a model that has an eddy-driven jet that is either too far equatorward or too weak, you never get these westerlies impinging on the tip of Greenland, and so you don't get tip jet events or sufficient numbers of tip jet events, and so this apparent northern peak disappears. So the CMIP models, though they all have Greenland, some of them don't get this three-peak distribution simply because the eddy-driven jet itself is either in the wrong place or it's too weak. So we did a little regression analysis. These are all of our simulations, and it seems to work pretty well. So if you have a weak jet at the latitude of Greenland, relative to the maximum jet strength, you get a weaker tip jet and a weaker northern peak. Seems to work pretty well. The blue are all of the CMIP 5. We haven't quite got a handle on the CMIP 6 yet, but we might be working on it. That's your interim right there. And the red is all of our different flattened topography simulations. All right. So it seems like these three preferred positions or regimes in the Atlantic, and forcing from various things, such as forcing from the stratosphere, forcing from mountains, etc., they don't affect the latitude of where these things occur. They just occur the probability of occurrence of the jet in one of those three positions. So that is a little bit different than talking about a systematic equatorward or poleward shift of the jet. It's also different if you look at it in terms of the spectral content of the jet latitude index. There is no 10-day timescale that peaks from such a thing. So when there's forcing on the Atlantic jet, you're affecting the frequency of these regimes and not so much the latitude of the regimes. The northern regime, or the preferred position, is not so much a dynamical thing as just the presence of Greenland. So the fact that you have Greenland and westerlies impinging on the tip of Greenland is what is responsible for this northern peak. And in terms of the CMIP, the model biases in jet latitude index appear to be correlated with biases in the climatological eddy-driven jet, both position and strength. Great, so I'm going to stop there. Thanks so much for your attention, and I'm very happy to take questions.
Are there any questions?
I'm just wondering about the vertical extent of the northern peak. If it's a tip jet, does that mean it's very shallow, and then the other two are barotropic?
Yes. That's exactly right. Mm-hmm.
Does this do the topography, or is there an ice sheet sitting on the topography that makes this stronger?
It is the ice sheet. I mean, the topography consists of the ice sheet. The stuff that's jutting out is the ice sheet, yes. Mm-hmm.
So Greenland melts and this will go away?
Yes. So Greenland melting on long time scales has more of an impact on the Atlantic basin than CO2 in Wacom.
Thanks. Are these jet position runs done with, are they fully coupled, or are they with observed SSTs?
They're with SSTs. I mean, fully coupled would have been rather expensive to run.
Do the models look any better? So all your analysis is based on, all the analysis you presented is based on so-called AMIP type run.
Yes, yes, yes. Mm-hmm.
Yeah, let's use the microphone.
So my question is about the first part of the talk, the pops.
Yay.
And looking at your movies, the troposphere looks disconnected from the stratosphere often. And then when it gets in the right phasing, then it gets a response or something. Is that a physical explanation, or what?
Yeah, I am still trying to figure that out. So of course there's planetary wave propagation from the troposphere to the stratosphere at certain phases of the year when it's westerlies which permit propagation. So that's an obvious physical basis. But why it happens at that certain phase of the mode and what it means, etc., I don't know, because I'm running in perpetual winter to not deal with seasonality, and what the timing of that phase is, and I don't know.
So what's the simple physics of this poleward propagation? Is it eddy feedbacks that do that, or?
No. So there's a couple of Sookyoung Lee and Steve Feldstein papers which say that baroclinic anomalies are feeding back on zonal mean, zonal wind anomalies, which cause the propagation. So that's not eddy feedback. It's there's a few papers on it. They say that they understand it. I haven't delved into the dynamics so much, but yeah.
It looks really robust, and
it's very.
I think there's some simple explanation or something.
Yeah, I don't find the papers to present a simple explanation, but what they say is that the baroclinic anomalies are feeding back on the zonal mean and zonal wind anomalies, and that's causing the propagation. But what sets the time scale and all of that, I don't know.
Okay.
Mm-hmm.
More questions, that's good.
In a given season, would the jet be sometimes in one of these positions and preferred positions and sometimes in another? And does the time it takes to go between those, can you relate that to some of the characteristic times you mentioned in the first part of the talk?
Yeah, so we are trying to figure out longitudinally varying pops. So I know that the Atlantic and the Pacific behave differently, and the propagation is not in phase in the two basins. In the North Atlantic, it seems a bit more complicated because of some of the stuff that I mentioned, right? So the answer is I don't know yet, but we're working on it. We're also working on the seasons question, which was your first question. But the trouble with coming up with seasonally varying pops is that you have chunks of 90-day segments. And so with era interim, right, with like 79 to 2015 or whatever, there's like 800 something EOFs. And I look at the cross correlations of every one of those EOFs with every other one of those EOFs. So to do that with chunks of 90-day data, which you then average across all of the 90 days, et cetera, is a lot of data management, and I'm not quite sure how robust the POP results are that come from that. Which is why I showed you perpetual winter, because it was a nice long integration, and you can look at cross correlations across 10,000 days or whatever, or 50,000 days. But with era interim, with seasonally varying, I'm not sure enough of my results to talk about them. Mm-hmm.
Yeah, I'm not sure if this is a relevant question, but the precipitation in Norway and Scotland are heavily impacted by the storm tracks, which
Yes.
are driven by the jet stream location.
Yes.
So it seems to me that if you're getting the jet stream location wrong in some of these climate models, then the precip in Scotland and Norway, which is the max for Europe, may also be wrong?
Oh, absolutely.
Okay. Yes, it is a relevant question. That's a problem.
Yeah, the storm tracks pretty much track with the jet. They don't do so at all time scales. They seem to do so after like 20 days. Like when the jet moves, the storm tracks move with the jet, but they take some time to do so. So yes, it is a very relevant question.
More questions? One more.
So people have related the timescale of EOF1 to the forced response, and have you or anyone looked at that for the POP timescales?
Yes. My postdoc is in the process of coming up with that plot. The trouble with the CMIP5 is that many of them don't have consistent data across the full troposphere and across the full latitude range. And we need daily data because we're looking at cross correlations at a time scale of 10 days. One of the things I didn't mention was that you need to pick a lag to get the POPs, and a reasonable choice of lag for era interim me kind of data is like between 10 and 15 days. So we need daily data for both the control and the forced simulation. So we're working on it.
So did you need more than one vertical level, or can you just calculate the pop on like 700 hectopascals?
You can do it at one level if you want, but I was hoping to do it for the full troposphere, just like I did it for these.
Yeah.
So
I
yeah,
have a lot of the data.
You
if
do?
Yeah.
well, we should talk.
More questions? If not, let's thank again Aditi.